Imagine designing an aircraft wing using the best equations available, validated wind tunnel data, and years of engineering experience. Yet the airplane still behaves unpredictably in flight. Some wings stall without warning, others vibrate, lose control authority, or fail structurally despite correct calculations. Engineers keep refining formulas, but the gap between theory and reality remains. One engineer realized the problem was not the wing, not the air, and not even the math. It was the way engineers understood and organized aerodynamic knowledge itself. His name was Walter Vincenti, and his work quietly reshaped how wings are designed and trusted. Walter Vincenti was born in 1917 in the United States, at a time when aviation was transitioning from a mechanical curiosity into a structured engineering field. Powered flight already existed, but aircraft design still relied heavily on empirical methods, accumulated experience, and incremental modification. Aeronautical engineering had not yet fully separated itself from experimental practice. This environment shaped Vincenti's intellectual development from the beginning. He pursued engineering studies with a strong emphasis on applied science rather than workshop-based design. His academic training combined mechanics, mathematics, and fluid behavior, reflecting the growing belief that aviation problems required analytical treatment rather than intuition alone. Unlike many early aviation figures who entered the field through piloting or manufacturing, Vincenti's formation was rooted in theory applied to real engineering constraints. After completing his education, Vincenti entered the US aeronautical research system during a period of rapid institutional growth. The National Advisory Committee for Aeronautics, NACA, had already been established as the central organization responsible for understanding the fundamental limits of flight. By the time Vincenti joined this environment, NACA's mission was clear: convert scattered experimental knowledge into usable engineering principles. Vincenti's early professional work focused on aerodynamic performance and engineering decision-making, rather than isolated component optimization. He became involved in research that examined how engineers justified design choices, validated performance claims, and managed uncertainty. This focus distinguished him from researchers whose primary goal was to improve a single parameter, such as lift or drag. One of the central problems Vincenti confronted was the lack of explicit reasoning behind many accepted design practices. Aircraft wings, control surfaces, and structural layouts often worked, but engineers could not always explain why they worked in a transferable way. Knowledge existed, but it was embedded in experience, undocumented assumptions, and local practice. This made it difficult to apply lessons learned from one aircraft program to another. Vincenti recognized that engineering progress depended not only on better equations or experiments, but on understanding how knowledge itself was generated, tested, and trusted. He observed that many aerodynamic decisions were based on precedent rather than explicit validation. This was acceptable at low speeds and limited scales, but it became problematic as aircraft grew larger, faster, and more complex. Rather than attempting to replace experimental work, Vincenti examined how experiments were used to support design decisions. He studied wind tunnel testing, flight testing, and analytical modeling as interconnected tools rather than competing approaches. His interest lay in identifying which methods produced reliable knowledge and under what conditions they could be generalized. This perspective led him to analyze engineering practice as a system. He examined how uncertainty entered the design process, how engineers compensated for incomplete information, and how safety margins were established. In aviation, these questions were critical because failure modes were often catastrophic and not easily reversible through incremental adjustment. Vincenti's work highlighted that aerodynamic knowledge was not purely theoretical nor purely empirical. It emerged from a structured interaction between models, experiments, and operational feedback. Engineers selected assumptions, simplified reality, and validated results through comparison with measured behavior. Vincenti documented this process carefully. emphasizing its role in producing reliable aircraft. During this period, Vincenti also became involved in academic teaching and research dissemination. He contributed to the training of engineers who would later work across government laboratories, industry, and universities. His approach encouraged engineers to question not only results, but the reasoning behind those results. Unlike researchers who focused on discovering new aerodynamic phenomena, Vincenti focused on how existing phenomena were transformed into engineering knowledge. He examined why certain aerodynamic principles became standard practice while others were abandoned. This required studying historical design choices, institutional constraints, and the evolution of testing methods. By the mid-20th century, Vincenti had established himself as a leading figure in the analysis of engineering knowledge production. His work did not aim to create new aircraft configurations or breakthrough technologies. Instead, it clarified how engineers decide what is safe, efficient, and reliable when complete information is unavailable. This contribution was particularly important for wing design. Wings operate under variable loads, changing flow conditions, and structural flexibility. Understanding how engineers evaluate these factors required more than aerodynamic equations. It required insight into how decisions are made under uncertainty. Vincenti's work provided that insight. He showed that aviation advances not only through better tools, but through better reasoning about how those tools are used. By making the logic of engineering explicit, he helped transform aeronautical design into a disciplined, transferable practice rather than a collection of isolated successes. This foundation would later influence how aerodynamic research was interpreted, taught, and applied across the aerospace industry. But its importance lies in its clarity. Aircraft safety and performance depend as much on how engineers think as on the equations they solve. As Vincenti's career progressed, his work shifted from observing engineering practice to formally structuring it. He began analysing how aerodynamic knowledge moved from laboratory research into operational aircraft. This transition was not automatic. Data produced in wind tunnels or equations derived analytically did not become useful simply because they existed. They had to be interpreted, bounded, and judged credible before designers trusted them. Vincenti focused on this gap between scientific result and engineering use. In wing design, this gap was critical. Aerodynamic behaviour varied with scale, Reynolds number, surface finish, and structural flexibility. Engineers routinely faced situations where test data conflicted or where analytical predictions failed outside narrow conditions. Vincenti examined how engineers decided which results to trust and which to discard. One of his key contributions was identifying different categories of engineering knowledge. He distinguished between fundamental theory, empirical correlations, design rules, and operational experience. In aerodynamics, these categories were often mixed without clear separation. Vincenti showed that confusion between them led to design errors, especially when wings were pushed into new flight regimes. This framework had direct implications for wing development. For example, a wind tunnel result might accurately describe lift behaviour at a given scale, but become misleading when applied to a full-size wing operating in turbulence or manoeuvring flight. Vincenti emphasised that engineers needed explicit criteria to determine when such extrapolation was valid. He also analysed how uncertainty was managed in wing design. Engineers rarely had complete information about airflow behaviour across an entire operating envelope. Instead of eliminating uncertainty, they contained it through margins, redundancy, and conservative assumptions. Vincenti documented how these margins were chosen and how they evolved as confidence in aerodynamic models increased. In practical terms, this work influenced how wings were certified and approved. Rather than relying solely on peak performance numbers, engineers evaluated robustness, how sensitive a wing was to manufacturing variation, surface damage, or unexpected flow conditions. Vincenti showed that a design that performed slightly worse on paper could be safer and more reliable in service. His research also clarified the role of failure in advancing aeronautical knowledge. Wing-related accidents were not treated merely as mechanical breakdowns. Vincenti analysed them as information sources that revealed limits of existing models. When a wing behaved unexpectedly, the question was not only what failed, but which assumptions had been wrong. This approach changed how post-war aeronautical research was conducted. Instead of seeking universal aerodynamic laws applicable everywhere, researchers increasingly focused on defining domains of validity. Wing theories were no longer judged by elegance alone, but by how clearly their limits were specified. Vincenti's influence extended into how design teams were organised. He emphasised communication between aerodynamicists, structural engineers, and test pilots. Wing behaviour could not be understood in isolation. Structural flexibility altered airflow, and pilot input altered load paths. Vincenti's work reinforced the idea that wing design was inherently interdisciplinary. As aircraft entered higher speed regimes, this perspective became essential. Swept wings, thinner profiles, and higher load factors amplified sensitivity to modelling assumptions. Vincenti's insistence on explicit reasoning helped engineers identify which aerodynamic predictions remained trustworthy and which required new validation. Beyond government research, his ideas spread through academia and industry. Engineering curricula began incorporating case-based reasoning rather than purely equation-driven instruction. Students learned not only how to compute aerodynamic forces, but how to judge whether those computations applied to real aircraft wings. Vincenti also contributed to the historical analysis of aeronautical innovation. He demonstrated that major advances in wing design rarely came from single breakthroughs. Instead, they emerged from gradual refinement of methods, better experimental discipline, and clearer reasoning about uncertainty. This challenged the myth that progress depended solely on genius or revolutionary ideas. By formalizing how aerodynamic knowledge was evaluated and transferred, Vincenti strengthened the reliability of wing engineering as a profession. His work ensured that improvements in performance did not outpace understanding, reducing the risk of catastrophic surprises in flight. This contribution was subtle but decisive. Aircraft wings did not become safer because engineers knew more equations. They became safer because engineers learned how to decide which knowledge could be trusted under specific conditions. That change shaped modern aeronautical engineering practice, and it remains embedded in how wings are designed, tested, and certified today. Walter Vincenti's most lasting impact on aviation did not come from a single wing, airfoil, or aircraft. It came from how he showed engineers to use knowledge itself when designing wings under uncertainty. By the mid-20th century, aircraft wings were no longer simple lifting surfaces. They were complex systems operating near structural, aerodynamic, and safety limits. Vincenti recognized that the central challenge was no longer discovering equations, but deciding which knowledge could be trusted, when and why. One of Vincenti's key contributions was clarifying how engineering knowledge evolves through use, not theory alone. In wing design, this was critical. Aerodynamic data from wind tunnels, flight tests, and operational experience often disagreed. Instead of treating these conflicts as failures, Vincenti showed that they were normal stages in engineering development. Engineers had to learn how to interpret imperfect data and refine it through application. This insight directly influenced how wings were designed for safety and certification. Rather than assuming wings were safe because they met theoretical criteria, Vincenti emphasized validation through multiple independent methods. Structural margins, aerodynamic stability, and failure modes had to be understood as interacting factors. This thinking shaped how engineers evaluated wing loads, fatigue life, and stall behavior, especially for transport aircraft where failure was unacceptable. Vincenti also highlighted the role of negative knowledge in wing engineering. Accidents, unexpected stalls, structural failures, and near misses were not anomalies to be ignored. They were critical sources of information. Each failure revealed gaps in existing models. In wing design, this meant learning from flutter incidents, load exceedances, and control anomalies to improve future designs. Modern wing safety standards owe much to this philosophy. Another area where Vincenti's thinking reshaped aviation was interdisciplinary coordination. Wing design is not purely aerodynamic. It involves structures, materials, control systems, and manufacturing. Vincenti showed that engineering failures often occurred not because one discipline was wrong, but because interactions between disciplines were poorly understood. His work encouraged integrated design teams, where wing geometry, stiffness, and aerodynamic behaviour were considered together. This approach became essential as aircraft entered higher speed regimes. Swept wings, thin profiles, and higher aspect ratios increased sensitivity to uncertainty. Small modelling errors could produce large real-world consequences. Vincenti's framework helped engineers recognise where conservative design margins were necessary and where innovation could proceed safely. This balance allowed progress without repeating catastrophic mistakes. His influence extended strongly into aviation education. Vincenti argued that engineers should not be trained only to apply formulas, but to understand the origin, limits, and reliability of the knowledge they used. In wing engineering, this meant knowing when aerodynamic theory applied cleanly, when empirical data dominated, and when assumptions broke down. This mindset shaped how generations of aerospace engineers approached design decisions. Importantly, Vincenti did not oppose innovation. He explained how innovation becomes possible after uncertainty is reduced to manageable levels. In wing design, this allowed new configurations, higher efficiency, and lighter structures, because engineers knew which risks were real and which were artifacts of incomplete knowledge. Progress became deliberate rather than accidental. By the late 20th century, many of Vincenti's ideas were so embedded in engineering practice that they were no longer attributed to him. Certification procedures, safety margins, design reviews, and validation protocols all reflected his thinking. Wings were no longer judged only by performance numbers, but by how well their behaviour was understood across all operating conditions. Walter Vincenti did not make wings faster by adding power or inventing new shapes. He made wings safer, more reliable, and more predictable by redefining how engineers reason about them. His legacy is not visible in a specific aircraft silhouette. It exists in the confidence engineers have when a wing leaves the ground, because they understand not only what it does, but why it does it. That shift, from designing wings by confidence to designing them by understanding, is what made modern aviation possible.